Right, so we're going to talk a little bit about the idea of capacitance, and this is kind of a bridge between the electrostatics and working our way into circuits. And so we need to talk a little bit about the devices themselves, and they're called capacitors. They're made up of alternating layers of conducting material and an insulator. And so there's a couple basic varieties. You've got parallel plate ones that are two pieces of metal with vacuum or air or some other material that's insulating in between it. Or they sometimes they take those two plates and curl them up in a coil, and so it looks like a little mini can. We're also going to have spherical capacitors, which is a sphere inside a sphere, and then a cylindrical one, which is like a rod inside a tube. And I'll show you pictures in just a couple slides. But basically, they're used to store charge or electrical energy in a circuit, and the amount of charge or energy stored is going to depend on the size or geometry, how far apart the plates are, and how much voltage is applied to the capacitor. And the insulating stuff in between is called a dielectric, and that'll be something we'll talk about a little bit later. But we're going to start off with capacitors that have vacuum in between. And so, like we said before, they store energy. So the quantity of capacitance, which has a symbol of capital C, is a measure of how much energy or charge is stored in a capacitor. You measure it in farads. Farads are huge, and you're most likely to see microfarads, nanofarads, and picofarads. And pico is 10 to the minus 12. Just heads up on that. And the dimensions on capacitors, while we're talking about units and things, dimensions are going to be millimeters. They're tiny. Micrometers, microns, things like that. So watch for some odd, tiny dimensions. And the capacitance, the actual equation, it's just a ratio between the amount of charge uh, and the applied voltage. There's a couple different configurations of this equation. You've got a parallel plate capacitor, which is epsilon naught area divided by the distance between the plates. You've got, for a sphere, two spheres, one inside the other, 4 pi epsilon naught, and the two radiuses multiplied together, where R1 is the inside radius of the inside sphere, and R2 is the inside radius of the outside sphere divided by the difference between the two. And I'm going to show you where both of those come from, starting with Gauss's law in just a minute. The last one, it's going to work a lot like the spherical capacitor when you start with Gauss's law and work your way through. But the equation there is the capacitance is 2 pi epsilon naught times the length divided by the natural log of the outer radius over the inner radius. And those are all starting from Gauss's law, and I'll show you that in just a second. All right, so we're going to talk about parallel plate capacitors and finding capacitance of the plates. Now, this is really closely tied to the two sheets of charge or two charged plates from the previous chapter. And so this is an application of that. So you're going to see some of the same formulas that we used in the last chapter. So we start off with what's the field close to a conductor? And you'll remember it is sigma over epsilon naught, where sigma is the charge density and epsilon naught is the permittivity of free space. And another one that'll probably look familiar is volts is equal to the electric field times the distance between the plates. When you plug in the equations, you'll kind of combine them, you're going to get volts is equal to sigma d over epsilon naught. And hopefully you remember charge density is going to be the amount of charge divided by the area. And so you end up with this equation where the voltage is charge times the distance, epsilon naught times A. And then, if you remember that capacitance is charge over voltage, then you get Q epsilon naught area divided by Q times the distance. And this works its way down to epsilon naught A over D. Notice that this is all geometry. So it is possible to find the capacitance of your parallel plates just simply by the geometry of the setup. You can also find it by the voltage if you use charge divided by volts, or by all of the geometry. So I have a quick example for you. All right, so in our example, we have a parallel plate capacitor that has a capacitance of 8 picofarads. And so a picofarad is 10 to the minus 12 farads. And this is going to be kind of common. You'll see nanofarads, picofarads, and microfarads. And then it has a distance of 3 millimeters. We want to make sure we have the right units in between the plates. And the question is, what's the area of each plate? And so we have the equation. The capacitance is epsilon naught A over D. And if we rearrange that, area is the capacitance times the distance divided by epsilon naught. Substitute all the goodies in here. 8 times 10 to the minus 12 farads. Our distance in meters. And epsilon naught is kind of a interesting unit because of the relationships between volts and charge and farads. The unit on this just gets renamed to farads per meter. And then if you do the math, what you find out is 7 square millimeters is what the area of each of the plates is. So that's 2 plates each with that same area. All right, so now we're going to look at a spherical capacitor, which is basically a sphere inside a sphere. And if you look at the illustration, you're going to notice that R1 goes from the center to the inside radius of the inner sphere, and R2 goes from the center to the inside radius of the outer sphere. And all of the charge is contained in between the two. There's a field in between the two. And we're going to use Gauss's law to come up with a nice relationship to find capacitance. And so we start with Gauss's law, and if you remember, for the sphere, when you do the work, you end up with E 4 pi r squared is Q inside over epsilon naught. And then if we want to find the voltage, we're going to have to do a little bit of an integral from R1 to R2 of the field dot dl. Plugging in what we got for the using Gauss's law. For E, and then remembering that that length piece dl is going to be the r hat dr. This simplifies down to Q over 4 pi epsilon naught from R1 to R2 of dr over r squared, which is equal to Q over 4 pi epsilon naught times 1 over R1 minus 1 over R2. C is Q over V. What we end up with is 4 pi epsilon naught R1 R2 over R2 minus R1. So here are the equations. Use them well. Talk to you later. Bye-bye.